Good morning. Today we're going to talk about Math 125 and in particular Section 6.2. 6.2 in our textbook is entitled the Standard Normal Distribution, but I want to take a look back before we go on to talk about the Standard Normal. But that is the official title of Section 6.2 in our text. Alright, we call in Chapter 5. In Chapter 5 was entitled Discrete Probability Distributions, as we all recall. And in the case of discrete random variables, well, you could take on finitely many discrete, meaning separate, discontinuous values of a random variable. So if asked to compute a probability distribution, it was often a simple matter to do so in a table type form. So let me make a note of that. Probability distributions in Chapter 5, meaning the discrete kind of case, probability distributions were often given in table form. You'll recall the probability of 3 boys and 4 births, etc. Okay? Well, in Chapter 6, we're going to start talking about continuous probability distributions. Let me talk a little bit more about what that means. In Chapter 6, Chapter 6 is actually entitled the normal probability distribution. And a normally distributed random variable is a continuous random variable. Here, random variables are continuous, not discrete. In other words, they take on values on a continuous scale. Okay? For example, if x is the speed of a car at a particular point in space, x could be the height of a child, height of a 6-year-old child perhaps. X could be, make up anything you like, I suppose, a body temperature. Right? All these values of x are on a continuous scale, or measured on a continuum, if you like. Right? We're not restricted to integer or even separate discontinuous values of x. Alright, since continuous random variables, like the normal random variable, which we'll talk about in detail later, if you've got a continuous random variable, that means you've got a continuous probability distribution. Remember, a probability distribution distributes one unit of available probability over possible values of a random variable. Well, how do we do this? Again, in a continuous, in the discrete case, it's easy to construct a probability distribution. You can make a list of possible x values and associate the probabilities with them based on our knowledge of probability. But in the continuous case, the table isn't going to work. You have infinitely many x values on any continuous scale. So what we're going to do in the continuous case, where a variable is a continuous random variable, I'll have an enveloping function I call a probability density function. And instead of listing probabilities in table type fashion, what I'll do is I'll consider my possible values of x on a continuous scale, and I'll make a link up between area under the curve and probability. Now let me make a note. Under a probability density function, the total area under the curve, or really bounded by the curve in the x-axis, is equal to 1, always. That's by definition of a probability density function. And of course that represents our one unit of available probability in any particular experiment. So if perhaps I'm interested in the probability that x is between A and B, I'm looking for the total area under the density function between A and B. Write that down, equals total area under the PDF, I'll just call it the curve, between A and B. Alright, so we make a link between probabilities and areas under curves. We'll need integral calculus to do this, but again, integral calculus is not a prerequisite for this course. Typically what we do in this situation in a first statistics course, to find probabilities of this type, we'll either resort to tables in the back of the book that were constructed with knowledge of calculus, or let our handy calculator, the TI-8384, grind out those areas under the curves for us. Alright, so that's in wide strokes what we're going to be talking about in Chapter 6. Again, Chapter 6 is entitled Normal Probability Distributions. Alright, normal distributions are a very special type of continuous probability distributions. Let me write that down. Normal is a special type of continuous probability distribution. Alright, a normal distribution is the proverbial bell-shaped curve. I'll draw a picture of that in a minute. In this bell-shaped curve, well, we'll always have symmetry, or say it's symmetric about the mean. And if you've got a smaller standard deviation in a bell-shaped or normal distribution, you've got a narrower bell. And of course, if you've got a greater SD in a normal probability distribution, you've got a wider bell. Alright, so let me do my best to draw a bell-shaped curve with these characteristics. Let's say I've got some mean, some unspecified mean, and I'll draw my bell-shaped curve just like this. Right. Bell-shaped in theory, these random variable values go off to positive and negative infinity in both directions. And don't lose sight of the fact that a normal distribution, one convenient way to think about it is to say you don't have too many scores piled up on the high end, you don't have very many scores piled up on the low end, but most random variable values, they tend to pile up around the mean. In other words, scores in a neighborhood of the mean are the most likely scores, eat up most of that area near the mean. Okay? Alright, note, there are infinitely many normal distributions. They are chiefly characterized, let me write this down, they are mainly characterized by the mean, which is where the bell is centered, and the standard deviation, of course, which measures the spread. Bigger SD, wider bell, smaller SD, narrower bell. Let me draw an example up here with your fresh screen. Let's say a class, let's say 3 different classes take an exam. And let's say class 1 in this exam results in a normal distribution of scores with a mean of 70 and a standard deviation of 10. Let's say class 2. Well, let's say class 2 takes the same exam, and again they have a normal distribution of scores. Let's say their mean is less, but their standard deviation is greater. And let's say also class 3 takes the same exam, and their scores are normally distributed also with a mean of 80 and a standard deviation of, let's say, 5. So what I can do is sketch a rough distribution of these scores based on this above information. Let's say class 1 has a mean of 70, so they're going to have a normal distribution, a bell-shaped distribution with a mean of 70. The bell is going to peak at 70. And again, we've got symmetry about the mean, vertical symmetry about the vertical line drawn at the mean, like so. Alright, so there's class 1. Let's draw class 2 in the same green. Class 2 has a mean of 60. Alright, so their bell, their distribution of scores is going to be shifted down to the left, and their standard deviation is higher, so we're going to have a wider, shorter bell, if you will. Still, the total area under the curve is going to equal 1. And in class 3, well, their mean is, let's say, 80. It's up here somewhere. Again, they've got a normal distribution of scores, a bell-shaped distribution of scores. The peak of the bell is higher, and notice the standard deviation is less, so we're going to have a narrower bell. Well, the moral of the story here, normal distributions are bell-shaped, always bell-shaped, and they're characterized, chiefly categorized by the mean equals the peak of the bell, and of course the standard deviation is the relative spread, measures the relative spread. Right? Mean and standard deviation, where is the center of data and how much is it spread? Alright, I want to talk about section 6.2 now. 6.2 is really the first section of this chapter 6. So section 6.2 is entitled Standard Normal Distribution. As we said earlier, normal distributions are a particular type of continuous distributions, and standard normal is a very special type of normal distribution. All right, by definition, the standard normal distribution, well, it's a bell-shaped curve because it's a normal curve, but we specify it has a mean of 0 and a standard deviation of 1. Alright, this standard normal is so special we reserve the letter Z to indicate a standard normally distributed random variable. Alright, so Z is a normal distribution with a mean of 0 and a standard deviation of 1. So when I see the variable Z in this context, right away I know that is reserved for the standard normal distribution. Alright, we can easily draw a picture of the standard normal. Well, it's your usual bell-shaped distribution, but it peaks at a mean value of 0. Alright, now the standard deviation is not so easy to visualize, at least with one curve. But just remember, the standard deviation gives you a measure of spread. Please remember, the total area under any normal distribution equals 1, and that's true for the standard normal as well. Total area under the curve, or really between the curve and the z-axis, is equal to 1. Alright, so if I was to ask you in this context, if Z is a standard normal random variable, what's the probability that Z is between a given A and a given B value? Well, again, what I need to do is find the area under the standard normal distribution curve between the limits A and B. Total area under the standard normal curve, I'll just call that the Z curve, between A and B. Alright? Alright, now what we're going to do is, again, use either tables in the back of the book, or more likely our calculator, our TI-83 calculator, will give us these areas, these probabilities, once we know the syntax of the TI-83 command. Alright, let me motivate these calculations with a bit of an example. And I'll refer to this example, this experiment, throughout the rest of today's online lecture. I'll say a large group of thermometers. Alright, a large group of thermometers at 0 degrees Celsius have temperatures that are normally distributed with a population mean of 0 degrees Celsius and a standard deviation of 1 degree Celsius. Alright, hopefully we can grasp the picture here. We got a large group of thermometers, and the temperature is 0 degrees Celsius. Now, some of these thermometers read high, some of these thermometers read low. Most of these thermometers hopefully read the correct temperature near 0 degrees Celsius. So what I'm going to do is draw a picture of this distribution. Now, when you're normally distributed with a mean of 0 and a standard deviation of 1, remember that automatically implies the standard normal distribution. Alright, so I'll draw a bell-shaped distribution that peaks at 0 degrees Celsius, and not too many thermometers readings pile up on the high end, not too many pile up on the low end. Most of these thermometer readings are piled up near the mean of 0 degrees Celsius, and I suppose that's a good thing. Okay? Alright, given this information, I'll say find the probability that a randomly selected thermometer reads between 1 degree Celsius and 2 degrees Celsius. Alright, we know our thermometer readings represent a standard normal. A normal distribution with a mean of 0 and a standard deviation of 1. This is what I seek. The probability that a randomly selected z-value is between 1 and 2. Well, in terms of a picture, I can easily draw a standard normal distribution peaking at 0. Let's say 1 degree Celsius is about here on our scale, 2 degrees Celsius is about here on our scale, and I claim this area that I've shaded in under the z-curve is the area I seek. Alright. Now don't panic because the TI-83 computes this. TI-83 or 84 will compute this for us. We don't need integral calculus, at least not yet. Alright, it's done with the normal CDF command. Okay. Now again, CDF stands for cumulative density function, and what it does, it accumulates all possible readings between 1 and 2, and then computes the area under that distribution function or density function. Alright, to find this command on our calculator, you hit the second button and hit your vars button. Again, you want to go to the distribution command. So hit second vars to get to that distribution command or menu. Let me do it here, second vars. And you'll see normal CDF. On my calculator, it's the second one on the distribution menu. We should be familiar with the distribution menu from chapter 5, of course. Now the syntax is this. The normal CDF command will compute the area under a normal distribution, in this case a standard normal distribution, between a left and a right bound of interest. So you have to enter in a left bound and a right bound for your particular application. In this scenario, it's between 1 and 2, right? Alright, so I claim the probability that z, a standard normal distributed variable, is between 1 and 2 is, well, you go to second, and then the vars, to get to the distribution menu. I'll call up normal CDF, cumulative distribution function, and of course my left bound is 1 and my right bound is 2. This will give me the area that I seek here. Alright, you enter this command and I get a 0.136, and that is the probability I seek. The probability that a standard normal distribution is between 1 and 2 is indeed 0.136. Alright, what we're doing here is we are given z-scores and we are asked to find the probability of being between those two z-scores. Let me do another quick example. Again, same experiment with the thermometers. Find the probability that at 0 degrees Celsius a randomly selected thermometer from our large pool reads between, let's say, minus 1.5 degrees Celsius and 1 degree Celsius. Well, again, we were told earlier, well, before I go on, I want to highlight something here. In this example, we are given limits for z-values, or I'll say z-scores, and we are asked to compute or find probabilities. Alright, we know that this large group of thermometers follows thermometer readings that have a standard normal distribution. Again, this may be redundant. Z automatically means standard normal. Alright, so I want the probability that Z is between minus 1.5 and 1. If I was to draw a picture here of the standard normal, the distribution of my thermometer readings, well, really I want the area under that standard normal curve between 1.5 and 1. Right. And again, the calculator will give us this with our normal CDF commands. So I'll hit second and vars to get to the distribution menu. Call up normal CDF command. And to use this command on our calculator, you've always got to plug in a left bound and a right bound. That is the syntax for this calculator. And finally, I'll get a probability of 0.774. Now remember, the total area under any normal distribution is 1, and that looks about right. If you're talking about between minus 1.5 and positive 1, it looks like, oh, almost all the area is swallowed up between those two limits. Let's try another one. Fresh screen here. Again, same experiment, same situation with this large group of thermometers. Find the probability that at 0 degrees Celsius, a randomly selected thermometer reads more than 0 degrees Celsius. Right. Again, the situation is similar to the previous two examples. We are really given z-scores or limits for z-scores, and we are asked to find probabilities. Well, you could make this more work than you have to, I suppose. If I draw a distribution of these thermometer readings, we've got not too many low readings, not too many high readings. Most readings seem to be near the mean of 0 degrees Celsius. Well, if you want the probability that a thermometer reads more than 0 degrees Celsius, we know the total area under this z-curve, or any normal distribution, equals 1, representing our 1 unit of available probability in any experiment. Well, if you want more than 0 degrees Celsius, basically I want all the area under the z-curve above 0. And of course, by symmetry, we know that's going to be 0.5. Right? You know that the z normal, standard normal distribution, or any normal distribution, is symmetric about the mean. So I can claim the probability then that z is greater than 0. Since 0 is the mean, I claim that's going to be a half. Alright, let's say we didn't know that, and we want to use the normal CDF command to figure this out. Well, the trouble is, with the normal CDF command, you've got to put in a left boundary, and you've got to put in a right boundary. That is how the syntax is designed on the TI-83 or 84. Well, clearly, if I'm looking for this area here, my left boundary is going to be the mean value of 0. So I can plug normal CDF I can plug in a left bound of 0. And what's my right bound going to be? Well, theoretically, this curve goes off to infinity to the right. And how am I going to represent infinity on my calculator? Well, our author has a practical solution for this. For positive infinity, our author suggests using the value 999,999,999, right? All right, so I'll use this as our best approximation for infinity. That's an approximately equals sign there I'm trying to write. Okay. Infinity will be approximated with this value, 999,999. And if I punch this out, well, I get approximately 0.5. Actually, my calculator gives me 0.4999999 off to 12 or so decimal places. Alright, so either using a little finesse and recognizing symmetry, or grinding it out with our normal CDF command, I can arrive at that probability pretty easily. Let's try another example of this, our fourth example of this. Again, same experimental situation with the thermometers. We've got a large group of thermometers with at 0 degrees Celsius, and I'll ask to find the probability that at 0 degrees Celsius a randomly selected thermometer reads less than minus 1.25. Well, if it's 0 degrees Celsius out, maybe that's a bad thing to read less than negative 1.25 degrees. Your thermometer would then be reading too low, but I suppose it could happen, and we want to find that probability. Again, here we're given z-scores, or limits for z-scores, and we are asked to find probabilities. Alright, of course, as we know, our thermometers follow a standard normal distribution with a mean of 0 and a standard deviation of 1. If I want the probability that a randomly selected thermometer reads less than minus 1.25, I seek the area under the standard normal curve below z equals minus 1.25. Alright, so let me write down what I seek, the probability that z is less than minus 1.25. This is the quantity I seek, and this quantity is this area, this shaded in area under the standard normal curve. Now remember, to use your normal CDF command, you've got to put in a left bound and a right bound for z. Well, of course, my possible z values theoretically go off to negative infinity, so I claim the probability that z is less than minus 1.25 is indeed the probability that z is between negative infinity and minus 1.25. And as you might guess, we're going to use our normal CDF command under the distribution menu. Well, you've got to put a left boundary. Well, again, your calculator does not have a negative infinity button or command. Our author asks us to use negative 999,999 as our approximation for negative infinity. So negative 999,999 will be our left bound, and our right bound will be negative 1.25. Alright, so approximating negative infinity in this fashion, I can punch out these values on my TI-83, and hence this probability turns into 0.015. So roughly 10% or 11% of thermometers will read less than this negative 1.2 value. Alright, so we've done 4 examples of finding probabilities given z-scores. Now we're going to work it in reverse. And it's going to involve a new command on our calculator. Well, instead of being given z-scores and finding probabilities, let's say we're given probabilities in terms of areas, and then being asked to find z-scores or z-values. Again, we've got the same scenario. At 0 degrees Celsius, a large group of thermometers have readings that are normally distributed I'm squeezing this in here, forgive me. At 0 degrees Celsius, a large group of thermometers have readings that are normally distributed, again, with a mean of 0 degrees Celsius and a standard deviation of 1 degree Celsius. Alright, here's the real deal here. Find the thermometer reading that separates the bottom 80% of readings from the top 20% of readings. Alright, so now we're working this in reverse. We're given probabilities and asked to find the z-scores. Well, what do I mean by we're given probabilities? Well, if we want to set it up so that you want to separate the bottom 80% from the top 20%, well, I claim there is a z-value, there is a thermometer reading, I'll call it question mark, that separates the bottom 80% from the top 20%. In other words, the probability of getting less than that reading is going to be 0.8, and the probability of getting above that reading is going to be 0.2. So here we are given probabilities in terms of areas and asked to find z-scores, kind of working our first 4 examples in reverse. Alright, to find this z-value, we're going to use a new command on our calculator using the inverse norm command. Invnorm, if you will. And the syntax for inverse norm, I'll call it, is that you have to plug in a left area, or an area to the left of a given z-score. This returns the z-value with an area of let me write this down. How am I going to phrase this? Returns the z-value with a specified area to the left. I'll call it left area under the standard normal curve, or z-curve. Okay? Alright, so if I want the z-value that cuts off the bottom 80% from the top 20%, I'm going to use inverse norm and plug in 0.8 because that's my area to the left. Alright, that's also under the distribution menu. If I hit second, vars, to get to the distribution submenu, it's actually the third. On my calculator, it's the third function down on this distribution list. Alright, so call up this command into your home screen. Plug in 0.8 for my area to the left, and I get 0.8416. I'll call it 0.842. 0.842. So that tells me a Z value, a temperature reading of 0.842 will separate the bottom 80% from the top 20% of all thermometer readings in this experiment. Alright, one more, we'll call it a day. And again, we're working our first 4 examples in reverse. Here I'm going to be given a probability in terms of an area under the standard normal distribution, and we will be asked to find a probability. I'll say find the thermometer reading from all this large groups of thermometers that separates the bottom 2.5% and the top 2.5% of all readings. All right, never hurts to draw a picture in these situations. Let's draw a standard normal curve. Z is a standard normal, bell-shaped curve with a mean of 0 and a standard deviation of 1. All right, I'm looking for 2 readings here. I want to separate the bottom 2.5%. Well, I'm going to exaggerate for demonstration purposes. I'm going to say that value is down here. It's some z-score, I'm not sure what, but I know that the area to the left of it is 2.5%. Now in decimal, 2.5% is of course 0.025. And notice I'm going to want a similar reading on top. I want to cut off the top 2.5%. So I'll draw another question mark here. This specifies a top z value such that the top, the area to the right of that thermometer, the reading to the right of that thermometer reading is 0.025. Alright, to find this value here, well again, if you're in the standard normal case, all I need to plug in is inverse norm 0.025. Now again, the inverse norm command specifies area to the left. So if I punch that out on my calculator, again, you could use second, get to the vars or the distribution menu, call up your inverse norm command, and plug in a left area of 0.025, and that command reads out a z value or z-score of minus 1.96. Now that's in degrees Celsius, so this tells me that a temperature reading of minus 1.96 degrees Celsius cuts off the bottom 2.5%. Alright, how am I going to find this? Well, I suppose there's one of 2 ways I could do it. I could say inverse norm, but again I've got to put the area to the left in my inverse norm syntax. Well, I think we can see that if you've got a right tail area of 0.025 you've got a total area to the left of 0.975, do we not? So I could plug in inverse norm 0.975. Again, hitting your second button, getting to your distribution menu through the vars button, call up the inverse norm command and plug in 0.975. I'm running out of room here. It turns out this z value is 1.96. Now notice that is the opposite of the negative 1.96 value we got on the left edge. And I suppose if I was attentive and I realized that the bell-shaped curve has symmetry with respect to the mean of 0, I could have just computed this value right here and instantly wrote down 1.96 by symmetry on the right end. Alright, this concludes section 6.2 video lecture. Thank you.